So now we can actually talk about probability tree diagrams themselves, that we've talked about the multiplication counting principle. To illustrate this, we're going to use the same example as the previous section, in which we examined a longitudinal study about people using e-cigs and then observing whether they developed lung cancer or not. So the way to think about this is we're going to think about it as a two-stage probabilistic experiment. So stage one, whether a randomly selected person uses or used e-cigs, menthol e-cigs. And the second stage, so regardless of the outcome there, then we observe whether that same person developed lung cancer or not. And that we will estimate using the prevalence of lung cancer in this group. So what we'll do to create a probability tree diagram, we start with the first stage. And however many outcomes we have for this stage, namely we have 2. So either they use e-cigs, either they don't use e-cigs or they do use e-cigs. And this branching off represents the full spectrum of possibilities, because everybody fits into one of these two categories. And we determine the probability in each group of that happening. So out of the 200 people, 155 of them did not use e-cigs and 45 of them did. And you'll know you've done this step correctly because when you add them together, they should equal 1. So we've partitioned our sample space now into A and A bar. But now we move on to the second stage, where we observe either this person developing or not developing lung cancer. So, to be clear, from the group of non-users, then we determine how many didn't develop lung cancer and how many did. So, symbolically, this branch represents A bar intersection B bar, and this branch represents A bar intersection B. So from these people, so from these 155, we determine how many got lung cancer and how many didn't. So out of the 155, 151 did not, and 4 of them did. And you'll know we did this correctly again if these add up to 1, because we've taken the event A bar, the random selection of somebody who doesn't use e-cigs, and now we've partitioned that further. And we do the same thing for the other group. So we determined those who did use e-cigs, how many did not develop lung cancer. So this would be A intersection B bar. And those who did, which is A intersection B. So of those 45, 26 did not develop lung cancer, and 19 of them did. So now we've got all the probabilities we want and all the outcomes we want represented in our probability tree diagram. So we did this correctly because the total number of branches, so the total number of outcomes we have at the very end of the branching process should be the same number of possibilities for each stage multiplied together. So we had 2 for each, so we multiply those together. We have 4. So why is this so helpful? Well, now we can determine pretty easily probabilities of those who in the intersections. So, for instance, question: what's the probability that a randomly selected person both did not use e-cigs but still developed lung cancer? So what we're actually asking for here, so somebody who did not use e-cigs, that would be A bar, and still developed lung cancer would be there in the set B. So we're actually looking for the probability of A bar intersection B, which is, we can do it the traditional way, which is A bar intersection B, the size of that set divided by the size of the total set, and we know that there are just 4 people in that group out of 200, and that is fine. We can use it that way, but there's an even faster way to determine this using the probability tree diagram. So as an aside, can we use it that way? Well, remember, so this is a thought bubble. Remember that the probability of B given A bar is the probability of B intersection A bar divided by the probability of A bar. This is from the definition of conditional probability. If we can rearrange this formula this way, we'll multiply both sides by P of A bar. Probability of B intersection A bar is the same as the probability of A bar times the probability of B given A bar has occurred. Except we actually know both of these pieces here. P of A bar, I'll remind you, was already given here. That's the first probability along that branch. Probability of B given A bar is this probability. By definition, the way we constructed it is we took the number of people in that intersection and divided it by the total number of people in that set that has already occurred. We've assumed that we've selected somebody who did not use e-cigs. So we actually have conditioned on A bar, which means that finding the probability of that intersection is as easy as multiplying all the probabilities along that branch. In other words, our answer can be found as well as 155 over 200 times 4 over 155. These cancel out. And again, we get 4 over 200. So this is the same result. We did a little bit more work here and just in the setup, but in the long run, this actually does pay off faster than using the contingency table if we already have the probability tree diagram set up. And we'll discuss what this formula right here actually represents in the next video.